Our Father in heaven, we thank you for today. We thank you for everything that you've done for us. Ask you to bless the teachers and bless this lesson. May we understand everything they teach us, and may we have no network disturbances. In Jesus' mighty name we have believed and prayed. Amen.
Amen. Thank you so much.
Amen.
I don't remember whether, can you assist me? We are doing numbers. That's why I wasn't. We are doing questions and we are doing some numbers. Can we do those numbers, please? Anybody with solutions? Madam Jeffrey, did you write down the questions? I don't have them. No. The questions, I don't have them. It is one which we formulated. Girls, there is a question I left on the board. Who has an answer for it? Or who remembers that question and we discuss it, then we move on?
Teacher, I have the
Okay, read it for us and we discuss it and then we move on.
Okay. A bullet of mass 50 grams.
Mass was 50 grams.
Traveling at 200 meters per second is stopped by a sandbag. Is stopped by a sandbag after traveling for 2 seconds by the sand.
By 2 seconds, yes.
Determine the power expended.
Okay. So the power that was expended, it was power is given as work or energy transfer. Okay, let me refer to this. Energy transfer divided by time taken. So what was our energy this time? What was the energy of the bullet? How do we find this energy of the bullet?
In other words, what was the work done?
What did the bullet have? When you look at that equation, what was the energy of the bullet? It was moving. So what type of energy did it have?
Kinetic.
Kinetic energy.
So the kinetic energy of the bullet was given by a half mv squared. That is okay. So can we calculate that?
A half. And 5 times 50 grams.
50 divided by what?
1,000. 1,000.
1,000
times 2,000 squared.
times
200. 200 squared.
and 200.
200. What's zeros? Number.
Cross the zeros.
Yes.
What do you have?
Number 7. The answer is 1,000.
1,000.
1,000 joules.
Please.
So this was the energy that we're going to substitute here. Now the time taken. What was the time taken? How many seconds did that were required to stop that bullet?
2 seconds.
2 seconds.
2 seconds.
2 seconds.
So what is our power?
1,000 divided by 2.
500.
500.
500 what?
500 watts.
Watts.
That was our question. So that's how we are supposed to calculate that equation. Please, those who did not do, I hope you have understood. And we want to stop with the calculations for at least but for now, and we decide power is equal to force times velocity. So we have the mass and the velocity. Is that okay? So it will be 5 divided by 1,000 times 10 times 200. So that goes with that and that and that. Okay? This time it is wrong. This equation will not work like that because we are talking about a different velocity. This is velocity. This velocity was outside. It was not inside the whatever. The whatever. So that is not what we apply. Here we are applying energy lost by the bullet.
Laptop down.
That's the difference.
Chape, pull the laptop down a bit.
Oh, wants to sit down.
Thank you. Excuse me, teacher. I don't understand why you can't use the force times velocity.
Okay. This bullet was traveling outside, so it had kinetic energy. By the time it entered the sandbag, it had its potential energy as it entered that sandbag. Is that okay? So the total energy that will be lost by the bullet will be the total energy with which it entered with. That's why we are saying that what's the energy by which, what does the energy of the bullet, what does it have as it enters the sandbag? That it has that kinetic energy. And that kinetic energy is transformed into another form of energy. As it enters the sandbag, there are energy transformations that are going to be taking place. For example, there will be heat and so on, and sound and so on and so forth. So we are looking at the initial energy, and that is going to be lost by the bullet, and that is in 2 seconds, and that's why we use that equation rather than the FV. FV will be talking about this when the bullet is traveling outside the sandbag. I hope you get the point. That's the difference. Why we don't use that equation of FV. Because we actually don't know the velocity of the bullet in the sand. And number 2, even the velocity of the bullet in the sand is not going to be constant. It is going to be changing. I don't know whether you get that point. FV is used when the velocity is constant. But this is a changing velocity because the bullet will be retarding. Is that okay?
Yes.
Okay. So I think we are ready to progress. Is that okay, girls? Let me see. I think we have discussed the majority of this document. Is that okay? Yes. I think we are done with maybe energy transfer. That's what energy transformation. Yeah, we are supposed to be discussing energy transformation. Is that okay, girls?
Yes.
Where we are, energy transformation. That's what we are supposed to be looking at. I make it bigger. Okay. You need to see. Where do I click? Where do I click? Make it bigger. This one.
Just
Is this okay? It is too big. Okay, girls, we are discussing energy transformations. I hope you're together.
Yes.
Okay.
Yes, teacher.
I'm going to request one of you. Let me see. Madam Javi, select a reader for us and we explain this note. Sean is ready.
Okay.
Give Sean a chance. She's ready.
Energy transformations. Interchange of energy in the gravitational field. A body moving under the influence of gravity possesses constant mechanical energy made up of two parts. That is to say, mechanical energy, which is equal to kinetic energy plus potential energy, which is equal to constant. Thus, a particle projected upwards keeps on losing kinetic energy and gaining potential energy such that kinetic energy lost is equal to potential energy gained. At the highest point, the particle has no kinetic energy, but has maximum potential energy. When falling, it keeps on gaining kinetic energy, but losing potential energy.
Okay. So can we pause at least up to there? Let us discuss that. Concentrate. Let me remove this and I try to explain what I'm talking about. Because sometimes we need an illustration. Let me stop to share. Concentrate on the board.
Teacher,
You're muted.
Teacher, you're muted.
There's something I want to do. Let me first remove this. Okay. Can we see? Let us see here. Look at the board. We are saying that a body is projected vertically upwards. At this point here, when the body is projected vertically upwards, that implies there is something pushing it. So you give it an initial velocity. And when it is moving upwards, it will go to a certain height and maybe initially stop there. So for anybody that has been given an initial velocity of, say, V, that's the initial velocity, then its kinetic energy at the point of projection will be a half mv squared. That will be the kinetic energy at the beginning here. So as it is moving upwards, it is doing work against the force of gravity, or it is doing work against its weight. Am I making sense?
Yes, teacher.
Yes. It is doing work against its weight. So what will happen that in its motion, this body will have potential energy, it will have a gain in potential energy, but it will have a drop in kinetic energy. So the kinetic energy will be decreasing, but the potential energy will be increasing. Is that okay?
No, teacher, how is the kinetic energy reducing yet it's going?
How is it?
Is the kinetic energy yet it's moving?
Because it is doing work against its weight. I don't know whether I talked about that. Where is the force of gravity acting?
Downward.
It is always acting downwards. So when you try to lift anything up, you are going to be doing work against the force of gravity. Is that clear?
Yes.
So this work comes from somewhere. We call it that initially when you are projecting something upwards, you give it a velocity. And that velocity, because it is motion, the total energy you have given it will be equal to the kinetic energy. At this point of projection, because it is on the ground level, the potential energy is zero. Why is it zero? Because the height is zero, isn't it?
Yes.
Yes,
Suppose
teacher.
here the height is 0. So as the height goes on increasing, as it is moving upwards, it is gaining what is it
Potential
gaining? Potential energy, because it is moving out from its original position. But what is happening to the kinetic energy?
Losing kinetic energy.
What is happening to the kinetic energy?
It's decreasing.
When it decreases. So when it reaches the maximum point here, let us call this maximum position. At maximum position, that's the highest point it can reach. What will the body be having?
potential energy.
Maximum potential energy.
Maximum potential energy, which will be given by mgh. So that will be the height. But what will be its kinetic energy?
0.
It will be 0. Why is it 0? Because the velocity will be 0. Is that okay?
Yes, teacher.
So the mass is the Q if the body is now coming down. When the body is coming down, what will it be losing?
Potential
energy.
Potential energy.
It went up, reached a certain height, and it came back down, isn't it?
Yes.
So what made it come back down? Why did it come the gravitational force that was pulling it down. Is that okay? So that implies that when you throw this pen, it at the point of projection, this is the point where you throw it from. It has the potential kinetic energy. And it goes on climbing up and up and up and up. That is, it moves further and further away from the point where you threw it from until it reaches a certain maximum point, that's the maximum position or maximum height. And when it reaches that maximum height, what does the pen do? It starts coming back, isn't it? Yes. And as it comes back, its speed is increasing as it is coming back, isn't it?
Yes.
So, but when it was going up, its speed was reducing, isn't it?
Yes.
So when the speed will reduce, and when it reaches maximum point or maximum height, the speed becomes 0. When the speed becomes 0, the kinetic energy, which is given by this equation, ½ mv², where there is we will put a 0, and that equation becomes the kinetic energy becomes what? A 0. Is that okay?
Yes, teacher.
However, it has maximum displacement from the point. So the potential energy at this point will be given by the mass or the weight times the height. And that is maximum potential energy. Am I making sense?
Yes.
So when now the pen starts coming down, its height or its displacement from the point goes on reducing. It is coming closer and closer to the point of projection until that height becomes 0, isn't it?
Yes.
When the height becomes 0, what has happened to the potential energy?
Becomes 0.
The potential energy is becoming 0, but now it has maximum speed. So what is happening to the kinetic energy?
Maximum.
It is
The kinetic energy now becomes the maximum, isn't it?
Yes.
So is that okay with you?
Yes.
Okay. So those are the energy transformation that occur in a gravitational field for bodies that have been projected up and then they come back to the ground. The energy exchange is of that nature, and it is basically mechanical energy. So at any stage of this motion, the potential energy, the sum of the potential energy and kinetic energy is always the same. We have observed that in our notes. Let me go back to the notes. Jonathan Gray, can you read for us that statement? Mechanical energy is equal to the sum . Who can read for us where my cursor is?
Me.
You read.
Mechanical energy is equal to kinetic energy plus potential energy is equal to constant.
And that always is a constant. So that value does not change at any point or at any position of the motion of the body as it is describing its motion in the gravitational field. Okay? Is it okay with you?
Yes.
Okay. Now, next we are going to discuss the next energy exchange is what we refer to as the simple
Pendulum.
pendulum. Let us get another reader to carry us through a simple pendulum. You don't send me, just read.
A mass
freely suspended on a string forms a simple pendulum.
When the mass is pulled to one side and then released, it swings between extreme points A and C. It has a maximum potential energy of A and C, but zero kinetic energy there. At point B, the kinetic energy is maximum while the potential energy
Is minimum there. Since mechanical energy is conserved, it implies that a simple pendulum would swing forever with a constant amplitude. However, in practice, the amplitude keeps on decreasing until it's completely zero, i.e. it stops. This is because of 1, air resistance, and 2, friction at the point of support.
Okay.
So you have seen the energy changes that take place.
Yes.
Simple pendulum. Let me draw it here. So from what you have read, if you release the super pendulum from this position, it will swing up to this end. Okay. Now, if it is at rest in this position, what energy does it possess at that point?
Potential energy.
Potential energy. Okay. Possesses potential energy here. Now, as it leaves this place and swings to this point, the potential energy is increasing or decreasing?
Decreasing.
Now, the height, because the height keeps on reducing, as this pendulum bob leaves that point, you can see if I take this to be the height from the central part of that spherical ball, the height keeps reducing. We are measuring the height from this point. This is the reference point. So the height keeps on reducing. Therefore, the potential energy reduces because we know that potential energy is equal to
MG.
This is MGH, right?
Yes.
From the principle of conservation of energy, if the potential energy is decreasing, where is that energy going?
Being transformed to another form of energy.
Is it transformed into
Kinetic
energy.
what form of energy?
Kinetic
Kinetic energy.
Into kinetic energy. So for all positions between this point and this point, it possesses both kinetic energy and potential energy. Kinetic energy is equal to 1/2 mv squared. Now, when it hits this point here, B, what potential energy has it got?
Zero.
Potential energy here is 0. Okay? Potential energy is 0. And therefore, kinetic energy at this point in the middle is maximum. Okay?
Yes.
Is that clear?
Yes.
It's maximum when it is in the middle. Then beyond this point, as it moves to this end, what happens?
Potential
energy
increase.
changes to potential energy.
The potential energy begins to increase as the kinetic energy does what?
Reduces.
Reduces. So here kinetic energy reduces, potential energy increases until potential energy is again maximum at the extreme end. So potential energy is maximum at the ends, both at A and C, while kinetic energy is maximum in the middle. Okay. So using that concept, we are able to we can actually calculate even how high it is. We can determine the maximum speed of that pendulum bob, and then also you can determine kinetic energy at any point of the motion. Like you have read, there are two factors here which are preventing, which are causing it to lose. Cause the amplitude to keep reducing. Air resistance is one of them. Okay, that because of air resistance cannot continuously return to the original height. It will the height will keep dropping as it keeps swinging until it eventually comes to rest in that position. Okay.
Yes.
So Mr. Sage over here wants to demonstrate what we have been talking about. Maybe we stop to share. Stopping the share. So girls, do you see what we have here?
No.
You can only see the string.
Does it possess?
Potential
energy.
Does potential
energy.
Is that okay?
Yes.
Now let's release it and we see, because if it does not have potential energy, it will not move, but it has potential energy, and that energy is now going to make it move, and it is going to transfer this energy into those, because it is moving. So the moment it starts moving, the potential energy is going to be converted to what energy?
Kinetic energy.
And then it will start moving. Is that okay?
Yes, teacher.
Number will continue swinging if it is not affected by any other forces. If this experiment was taking place in a vacuum, you know what a vacuum is?
Yes.
What is a vacuum?
A closed
without matter.
area.
It is not an area, it is a space without
Matter.
say the correct whatever. It is
Without
a space.
matter.
So if this experiment was being done in a space without matter or in a vacuum, that swinging would never stop. It will be a continuous swing. But now look at that swing. What do you observe about it?
It keeps
Slowing down.
It's slowing down.
That speed reduces.
It is keeping, it is slowing down. Now you observe what also I did. I am swinging this pendulum, and at the beginning, when it has a lot of potential energy, it is swinging in a specific direction. Is that okay?
Yes.
Yes. There's energy that swing